So welcome back. As I was telling you last time that now we will be doing another topic in which we can do the stability analysis of a transient system, and that is called as a very important topic, phase portrait. Okay, and specifically we will be doing the stability analysis in this method, and this is really appreciated and enjoyed in the electrical engineering course, and it is a very important topic for them. So consider a few pre-assumptions that we'll be having the system of this form only now, x dot is equals to ax, and that too very specifically for the sake of simplicity, I should say extreme simplicity, we'll be only dealing with 2 by 2 system so that it becomes easy for us to calculate eigenvalues and eigenvectors. Okay, so we'll be doing it for only a 2 by 2 system. That's it. Consider that A equals to, so what I'm going to say is that using or the learning outcomes of this particular module will be that on the basis of the nature of eigenvalues of A matrix, you can infer about the stability of the system, which is dependent on time. So consider, let us take one simple example. A is equals to minus 3, 1, 1 minus 3. And you need to find out its eigenvalues first. So when you will find out its eigenvalues, you would actually need what? You would need characteristic equation, which would be lambda I minus A ka determinant equated to 0. So in a way, what I'm saying is lambda I minus A. So it would be lambda plus 3, minus 1, and this will also be minus 1. Iska determinant chahiye, it would be equals to lambda plus 3 square minus of 1. So it becomes lambda square plus 9 plus 6 lambda minus 1. So this is lambda square plus 6 lambda plus 8. Okay. And if you solve it further, you will get your lambdas or roots to be equals to, let's say lambda 1 equals to minus 2 and lambda 2 equals to minus 3. In that way, you can get eigenvalues for any given 2 by 2 matrix, right? You can get eigenvalues for any given 2 by 2 matrix. Now, based on what type of eigenvalues you are getting, you can actually infer about the system or the stability of the system. Now, you don't have to go very deep into why I'm teaching this. It is only, let's say, a one-liner answer. And you can just make a table that you will be having two eigenvalues first. Remember that. You will be having two eigenvalues. Okay. Because our system is a 2 by 2 system, let's say it would be having two distinct eigenvalues. The case when the eigenvalue is the same, you would take it as a case included in these eigenvalues. So we will have two eigenvalues. Okay. Now there are two possibilities. Your eigenvalues can be real or they can be complex. Okay. अभी तो हमने देखा कि we were getting only real roots. But it was possible to have complex roots as well. So eigenvalues can be real, eigenvalues can be complex. Now, if both the eigenvalues are real and positive, if both eigenvalues are real and positive, then our system is unstable. Okay. Although it is called as a node which is unstable. So unstable node क्या होता है? We call it as unstable. Remember, only unstable is fine for you. If both are negative, then the system is said to be stable or asymptotically stable. If one of them is positive and the other is negative, in case of real eigenvalues, then we got what is called as a saddle point. Okay, so ये तो तीन conditions हैं real values के लिए. So we can have real values which are both positive, system will be unstable. We can have real values both are negative, the system will be stable. We have real values which are one positive, one negative, then it would be a saddle point. So when you have real values or real eigenvalues, you got what is called as a node point at origin, and that node can be a sink, मतलब चीजें उसके अंदर आ रही हैं. It can be a source, चीजें वहां से बाहर जा रही हैं, or it can be a saddle point. It means in one direction it is working as a sink, in another direction it is working as a source. Okay. So if something is going out in infinity, we call it as unstable. If something is coming in at, like, from all directions coming in at a point, we call it as a stable node. But if in one direction it is coming in and the other direction it is diverging out, we call it as a saddle point. Okay. Next, what if we have complex roots? So you know that when we will be having complex roots, there are two possibilities. That you will have a real part and plus minus the imaginary part. Okay. So whenever you will have two eigenvalues, definitely, for sure, the imaginary part will be present in the conjugates. You don't have to look at the imaginary part. You only have to look at the real part. So when you have the eigenvalues which comes in complex, the system is called as a spiral. When the eigenvalues are both real, we call it as a node. When the eigenvalues are complex, we call it as a spiral. Now, this spiral will be stable or unstable, depends on the sign of the real values. So this spiral will be stable if your real part is negative, and your spiral will be unstable if your real part is positive. And in case your real part is equals to 0 and you have pure imaginary values, then your spiral will come into the form of circle or ellipse. Okay, the closed trajectories, not coming to the node at all, or not coming to the origin at all. And for that, I would like to share with you, first of all, a question from your question bank, in which it is expected that for the given matrices, as you can see flashing on your screen, you have to do the stability analysis. You have to find out whether the system is a stable, unstable, it's a saddle point, it's a spiral, or what. And you also have to portrait the, or draw the phase portraits. So phase portraits are nothing but it's like you are plotting eigenvectors, taking one eigenvector on x-axis and the other on the y-axis, and you are then spanning it for some values of x and y. What I'm saying this, you will get to know that. But as of now, I will share another screen with you, which is more or less a simulation type. So I would share the link of this particular thing in the description of this video. But as you can see over here, we have certain things right over here. Let me just clear everything as of now. And here we have the A matrix, and we can actually put in the values of the required matrix in it. And you can find out the phase trajectories right over there. So this is my companion matrix, or the matrix which I'm going to take now. So you see that I would be changing the values of A, B, C, D, which is this one is A, this is B, this is C, this is D. And अगर आपने पीछे जो मैंने matrices बताई थी उसका एक screenshot लिया हुआ है, then you will get to know that our first matrix is -3. Let me just take it to -3. 1, 1, -3. So this is a nodal sink, and as I told you that sinks are always stable. You see that all lines are coming towards this node, and this is only a few trajectories mentioned. There can be infinite trajectories, like, as you can, using your arrow, I can draw this. So this one is from mathlet.org. This is some Stanford or MIT's platform. But you can see that at any point I'm clicking, I'm getting every arrows which are towards the center. So that's why we call this particular point as a nodal sink or stable. This system, which is represented by this matrix -3, 1, 1, -3, is a stable system. Let us take another matrix. Let us take another matrix. It is 3, -1, -1, 3. So let me just flip the signs. Now another matrix. 3, -1, -1, and 3. So for this particular case, you would see that your eigenvalues will be both positive, 2 and 4. In the previous case, we were getting our eigenvalues to be negative, -2 and -4. But in this case, we have eigenvalues which are both positive, 2 and 4. Both are real and positive. And now you can see, just अभी ये मैंने जो आपको बताया, if we have both eigenvalues and both are positive, then the system is unstable. You see that it is written over here, nodal source. So sources are unstable. You see, all of the values will be going out. No matter where I click, all the arrows will be coming out or going out of this origin, going to infinity. अनंत में खो जाएंगे. Fine. So using this or just looking at this phase portrait, इसे हम बोलते हैं phase portrait, जो ग्राफ आ रहा है. Just looking at this phase portrait, आप किसी भी सिस्टम के लिए बता सकते हैं whether this system is a stable system, unstable system, or what type of a system is it. Now let us move ahead. Try with 1 minus 3 minus 3 1. So we have another matrix which is 1 minus 3 minus 3 1. Let me just switch to that particular case. We have 1, then we have -3. So you see in this case, if any one of the eigenvalues becomes 0, it becomes degenerate. It is 1 minus 3 minus 3 1. So we have one eigenvalue which is positive and the other eigenvalue which is negative. And in that case, you see, we are getting a saddle point. In one direction, you see, if we go by this direction, which is minus x equals y, this line, you see, x equals minus y here, you see that it is going away, it is going away, it is going away. But if I take this point, it would be coming towards the center. It would be coming towards the center, towards the center. So that's why we say that it is a saddle point. In one direction, it is coming to it seems as if it is coming towards the center. In the other direction, it seems as if it is going away from the center. Okay. So this is a saddle point. Just by knowing the values of the eigenvalues, you can infer about the state of the system. Done? Move ahead. Let us take another example. So I will just share the link with you. You can use your own matrix. You can try with your own matrix. Another matrix is 0 minus 2 2 0. So let me try that as well, because the question bank has been designed for a variety of questions. So it is 0 minus 2 2 0, 0, then minus 2, 2, and 0. You see, we are getting it is 0, it is 0.5. You see, this is just a center, total center. We are having purely imaginary eigenvalues, and I told you that when we have purely imaginary eigenvalues, we have spirals, or spirals which will not come to the center. They will be stable spirals. We call this as a center, not as a spiral even. We call this as a center. So when you have purely imaginary eigenvalues, you call that as a center. Okay, and let us take then another matrix which is -1 2 -2 -1. Let me just change this. -1 2 -2 -1 -1. Then we have 2 -2 and -1. In this case, you see we are getting a spiral sink. A spiral, definitely it was supposed to be a spiral. Let me just take this there. It is to be -2. So -1 2 -2 -1. You see that the eigenvalues are complex, and the real portion is negative. That's why it is a spiral sink. Sink means it is a stable spiral. Whereas for another case in which we have 1 2 -2 1, let us do that one. We have 1. Okay, let me take this 2 -2, and this one is 1. You see, in this particular case, the real parts is 1, and therefore it is a spiral source, or it is spiral which is not stable. It would go out or will go to infinity as the time will proceed. So this system is not a stable system. So just by looking at the eigenvalues of the system and making the eigenvectors and using them to make phase portrait. So here x and y are nothing but eigenvectors. और उसे आपने एक दूसरे के respect में plot किया, you are getting phase portraits. Okay. So in exam, it is expected that at least you are knowing how you will relate the stability to the given eigenvalues. Fine. So this is all. I think this particular thing was on question number 43 of your question bank, and this part is from unit 3, I guess. Anyways, so you got to know a lot of things about just a 2 by 2 system, a matrix, and using linear algebra, which we already know from your semester 3 and 4. But you can simply use that concept of linear algebra and find out whether the system will be stable, spirally stable, it would be a sink, it would be a source, whatever it would be. Just by analyzing the nature of the eigenvalues, you can do that. Okay, so that's it for the state space. Only one more topic is left in which we have to do what are the characteristics of state matrix, and that we can do in this particular course itself. Let me just switch to my pen and paper screen. There are a few properties of state matrix or transition matrix to be in particular. So there are a few properties of transition matrix. Transition matrix. Okay, so remember that our transition matrix is given by phi of t, and we write it as it is equals to some e of 2. This is corresponding to a system which is x dot is equals to ax. So that's how we'll get the transition matrix. 2-3 classes back, I was just telling you this thing, where you can calculate phi of s to be some si minus a inverse. But as of now, our focus is on e to the power at or the transition matrix only. Okay, even bu is not required in this case. We just need x dot equals to ax. Okay, first thing, what is phi 0? So you know that phi 0 has to be equals to, at the place of t, you just have to put 0. So it means I have to multiply a 0 vector with this matrix. It is e to the power 0, so it has to be identity. Property number 1. That phi 0 is equals to a to the power a0 or e to the power a0, which is equals to identity. Second property, phi of minus t. I can write this equals to e to the power a of minus t. Okay. Then I can also write this as e to the power at or its inverse. So I can actually say that it is nothing but equals to phi inverse of t. So phi of minus t is equals to phi inverse of t. Property number 2. Property number 3. Phi of t1 plus t2. It is e to the power a t1 plus t2, which will be e to the power at1 dot e to the power at2, which will be nothing but phi t1 into phi t2. Remember? So this is property number 3. Then on this property itself, you can have the fourth property. Let's say phi t raised to the power n. So we can have e at raised to the power n, which is nothing but equals to e a n t. So which is nothing but equals to taking phi of n times t. So you are taking power of this state transition matrix or the transition matrix. It is just as if in the input you have multiplied with n. That's it. Okay. Then e to the power at, and you want to take the derivative of it, it would be nothing but a matrix and this matrix. That's it. Okay. A matrix dot e to the power at. And the last property, so this is, let's say, the fifth property. The sixth property is quite simple. It is phi of t1 minus t2 multiplied with phi of t2 minus t1 minus t2 and phi of t2 minus t3, let's say. Okay. And this will be equals to, let's say, let us try to find out. It would be e to the power a t1 dot e to the power minus a t2 dot e to the power a t2 e to the power minus a t3. तो ये देखें ये दोनों ऐड होके कैंसिल हो जाएंगे t2 और t2. It would be e to the power a t1 minus t3 only. So we can write that this is nothing but equals to 5t1 minus t3. t1 minus t2 and t2 minus t3 is just t1 minus t3. So these are a few properties of your transition matrix. So we have done quite a good amount of work on transition matrix or state space analysis as of now. Okay, so what we have done, formulating state space equation, solving state space equation, okay, the eigenvalues approach or the lambdas approach, and from lambda determining the stability, and the last, some properties of a transition matrix. And with this, we finish our state space equation. Okay. That's it for today's class. From next time onwards, we would be taking some new topics which would be related to your unit 1. Thank you so much, all of you.